Now let us look at the next problem. An infinitely long hollow conducting cylinder with inner radius r by 2 and outer radius r carries a uniform current density along its length. The magnitude of the magnetic field as a function of the radial distance r from the axis is best represented by. Okay, now let us understand the situation. This gray shaded portion is the one, or is the cross section of the conductor through which current is coming out of it, and we assume that it is having a uniform current density J. Okay, now we have to find out the magnitude B as a function of distance r, where distance r can vary from the center within the conductor, then in between the conductors, and outside the conductor. Now in these three cases we will find out the relationship between the magnitude of the magnetic field and the distance r. Okay, and in all the three cases we will be applying Ampere's circuital law. Okay, Ampere's circuital law. Now the first case is where r is less than capital R by 2, that is, you consider a point which is inside the hollow. Okay, now at this point if we apply line integral of b dot dl, it will be 0, because mu naught it, if we find out, there is no current that is threading through this loop. Okay, since it is 0, there is no current which is threading through this imaginary loop, therefore the value of this is 0, which in turn means that magnitude is also 0. Now let us take the case of point which is inside the conductor. Okay, it is somewhere here. Now by symmetry we know that magnetic field at any point will be radially outwards. Okay, now if we apply Ampere's circuital law, B dot dl, which is equal to mu naught it, that is I threaded through the loop. Now this blue portion, this is the cross section through which current is threading. So let us first find out what is the threaded current. It will be current density J into cross sectional area of this blue portion, which is pi r square minus pi r by 2 ka square, right? So this will become pi r square by 4. This can be written as, it can be written as j pi r square minus r square by 4. If we substitute this value here, okay, then we will get b dot dl line integral as equal to mu naught j pi r square minus r to the power 2 by 4. And now b dot dl, if you take the line integral of magnetic field across this imaginary loop, it will be b into 2 pi r equal to mu naught j pi r square minus r square by 4. Okay, now this pi will cancel out, and we will have the magnitude b as mu naught j by 2 r minus r square by 4 r. Now this is the function of magnetic field as a function of r, where r is greater than r by 2 but less than r. Okay, so this we have to remember. Now the third case is wherein the point is outside the conductor, and by symmetry we know that magnetic field B will be radially out across each and every point on the imaginary loop, that is shown by the dotted circle over here. If I apply B dot dl, this is again B times 2 pi r, which is equal to mu naught I t. Now I t will be this portion of current that is flowing. Now the inner radius is r by 2 and outer radius is r. So the value of IT will be given by j pi r square minus j pi r square by 4, which is 3 by 4 pi j r square. Now we substitute this value of IT here, then we get B into 2 pi r equal to 3 by 4 j pi r square. This pi will cancel out and we are left with B equal to 3 by 8 j r square by small r for value of r greater than capital R. Okay, now if you look at all the three cases where r is less than r by 2, where r is less than r but greater than r by 2, and for r greater than r greater than capital R, in all the three cases the function, if you see, magnetic field is 0 up till this case. For this case it is 0. The moment you reach r by 2, you have some magnetic field and it keeps on increasing because the function is something like r minus r square by 4r. Okay, so it will keep on increasing with the value of r until you reach the surface of the conductor. Now from that point onwards, the magnetic field is inversely proportional to the distance r, so it will reduce. So this is the correct option.